So in yesterday's discussion, we had started off by talking about the asset price equation, right? That how is it that the asset price movements are defined in the structural credit risk model, which the framework for which was adopted by BSM in its 1987, 1991, and 1997 works, and finally which found its way in Gaudi's 2003 paper, which frames the very basic idea behind uh, so which frames the very basic idea behind Gaudi's 2003 paper, which the on which the entire Basel framework has been regulated. And the model on which this entire thing was based was known as the asymptotic single risk frontier model, or the ASRF model, right? The basic idea behind the ASRF model is that there is a single risk factor which impacts the the losses and the risks of the portfolio of a bank's business portfolio, right? So this is what the overall idea is. Now over here, what we were trying to do is we were trying to develop the we were trying to understand the very basic nuances of this model, right? So we were trying to understand how this model would have worked, and how what are the very basics which has brought in this particular structure. So from the very basic equation of this model, we started exploring the asymptotic single risk frontier model, following which we would reach the definition of PTCPD, point in time PD, and so on. So over here, as you look into this, so we explained interpreted the asset price equation in its most simplest form, right? Without using any mathematical equations or without using any mathematical derivations, we explored this equation. So we saw that the asset price movement is composed of a few important components. One is that there is an average percentage change in the asset value per unit of time, the average change. Then what we have is the total change in the time period. Then what we have is the Wiener process and the Brownian motion. So each of these components go into create the asset path equation. Now the next objective that we had over here was to derive the estimate for the probability of default. We said that if there is an obligor I who had, or if there is an ith obligor who had borrowed a certain amount of money from the bank, or who has a certain debt obligation, so this borrower would be a defaulter if the asset price is less than, or if the asset falls below the level of the debt obligation. So when we have this, when we talk about the PDI, the probability of default for the ith borrower, it is nothing but the probability of the asset path AI to fall below the debt obligation, right? So this is precisely what the idea is. Now the next thing that we need to do over here is the most important. So the next step is, once you have defined the probability of default like this, the next thing that we need to do is we need to we need to define the asset equation path. We need to identify that what are the factors which would identify the asset path of a borrower, the asset dynamics of a borrower. And that is where we said that to compute this, what do you require is the Ito's lemma. So the Ito's lemma is actually used to derive the path of the asset from a first order derivative or a first order differential equation to derive the path of that AT, something which we need to understand that how is this thing actually done. So over here, what we are to do is we need to understand that how this thing has actually been done. Right? So in order to do that, we explored the concepts of derivatives in the last class, and we saw that the derivatives of, so basically what we saw was that a function is initially a rule, which explains the causality between the independent and the dependent variables, right? And the derivative of a function shows the rate of change of the dependent variable with respect to one unit change in the independent variable. So this is what we have seen till the last class, right? Now over here, one very important part that would play a function that would play a very important part going forward is the fx equals to the log x function. So fx equals to the log x function. So fx equals to log x. So log stands for logarithms, right? So this fx equals to log x has a very specific relationship. Now log x function is defined only for the positive values of x, that is x greater than 0. For any values of a variable, for any positive values of a variable, this function is gradually defined, right? So the next thing that we need to understand over here is some basic properties of this log function. And from there, we need to relate it back to the asset equation that we have used over here. So basically what we get to see is, so let me just first talk about the logarithm function and then we will take it up. So fx equals to x is, sorry, fx is equal to log x. So this log function that I'm talking about over here, this log function is the logarithm. We all know what a logarithm is, right? A log function. A log function is a log transformation, which is generally used to define the overall behavior. So which is used to smoothen out. It's a function. It's a transformation which is used to smoothen out irregular movements in the behavior of a variable. So generally, if you have if you have too much of fluctuations in your system, what you do is you do a transformation. So the log transformation is kind of an ordinal transformation which just transforms the values of the variable, smoothens them out without changing their ordinal behavior. So one very important characteristic of a log function is that it is only defined for values of x greater than 0. For x greater than 0, the log function, the log x will be defined. So log function is not generally defined for kind of, it is not generally defined for negative values or for 0. So log 0, log negative values are undefined. So the function is undefined at negative values. So log x will be defined. Defined, right? Now with log x, there are certain characteristics of log x, of the log function. So suppose there are two variables, right? So one is x, there is another is y. Then the logarithm function would satisfy some of the following informations, uh, or some of the following characteristics. One of the major characteristics is that log x into y is equal to log a, sorry, is log x plus log y. Right? So this is one of the logarithm rules. Now the next rule that I have over here is log x by y. Log x minus log y. So these are some very basic fundamental ideas about logs. Now, one another important function over here is about the logarithm function is that that over here what we need to understand is that what is kind of the first derivative that y has. So, for example, if a function, if there is a function y which is equal to f of x, which is log x, then what is the rate of change in y if x changes by 1 unit? So this is what we need to understand. So what is the f dashed x? Or let's put it like this, what is the dy dx if y is equal to log x? So if y is a logarithmic function of x, then what is the dy dx, or what would be the rate of change of y with respect to 1 unit change in x, given that the actual change in, or the observed change in x is very small. So if x changes by a very small amount, log x changes by a very small amount, y also changes by a very small amount. So then the question that comes up over here is that what is the change in y with respect to the change in it? So over here, so what we want to do over here is we want to calculate this one. So let us see how this, or how can I map that rate of change. So dy dx is limit delta x tends to 0. So when I say delta x tends to 0, what I simply mean is the change in x is very small. F of x plus delta x minus f of x by delta x. So this shows the change in y, delta y. This shows the denominator shows the change in x. So it says that when the change in y is delta y, the corresponding change in x will delta x. So if x changes by 1 unit, the change in y is delta y by delta x. So the next part that I have over here, or the next part that I can see over here, is the following. So what I need to do is I need to first calculate over here x plus delta x. This is log minus log x. Log x. So this is of the type log x minus log y. So obviously what I can write over here is log x by y. And this is your x. Over here what you get to see, this is x. So over here, if you have a look into this, I can say that dy dx over here was image delta x tends to 0 log by delta x. So I'm not going into the log expansion and the series of this, the log expansion and the resulting series from here. So what we just need to do over here is I'll just show you the results. The final result after you solve this will be 1 by x. So the first order derivative of the log function is 1 by x. So over here, if we expand this series in the form 1 log 1 plus x, and we undertake a whole series expansion and then impose limit x tends to 0, it is only 1 by x which remains back, right? So, I mean, this gets divided with this particular delta x value. So it is only the one the first term, which is 1 plus x. So the other gets cancelling out, and they tend to 0 after a point of time. So it is only that dy dx remains back. So dy dx equal to 1 by x remains. So this 1 by x would obviously come once you start expanding this series of 1 plus x. So it is like 1 by x. So it is x plus x square by 2 factorial plus x square by 3 factorial, x cube by 3 factorial, like this it would go on. So ultimately everything tends to 0, only 1 by x remains back. So therefore what it says is that the first order derivative of y equal to log x is 1 by x. 1 by x. Right. So over here, if you think about this, so now let me think about it like this. So what is the total change in this y with respect to change in x? Right. So let's think about it like this. So if you see this, dy dx is 1 by x, right? Over here, the first order derivative of y with respect to x is this, equal to 1 by x. So what is the total change in y? So this shows what? The change in y due to 1 unit change in x. So now, what is the total change in y with respect to the total change in x? So to get that, what I need to do is, I just need to cross multiply dx. what I'll get is dy is dx by x. Now, if you have a look into this particular portion, you can relate this part back to the AT. So what we'll get over here is we'll get to see that dAT by AT, right? So this is nothing but what I can see is the left hand side is nothing but the d log AT, right? So this shows the d log AT over here. Right. So over here, when we started writing of the asset price equation, so just if we recollect the asset price equation over here once again, mu a dt plus sigma a dw. So from this logic that we have discussed over here, we can clearly say that the left hand side is nothing but d log at. Right. So we can obviously also we can what we can clearly say from here is that this is the d log at, right? So then the d log at is equal to mu a dt plus sigma a dw at. Clear? So once I have an equation of this particular form, right, then what I can do is I can actually apply the Ito's lemma to work with this. So now on this we can apply the next thing that we do is we apply the Ito's lemma to get a part of the equation. Now I am not going into the derivative parts. I'll just show you what the Ito's lemma is. And from there what we'll do is I'll talk about the equation, and from there I'll just directly show you the results. I'm not going to the derivation of the condition step by step. So I just needed to build this, just plug in this gap that where is this log function coming in. Now this is a very common transformation that we need to do, right? And please start working on your basic calculus and models, because when we go into the nonlinear modeling methods, like when we go into linear regression, logistic regression, decision trees, classification algorithms, and from there where when we start moving towards the neural networks, which I plan to cover. So neural network, bagging, boosting, and all these stuff. So there you need to have an understanding of these basic calculus methods. So without an understanding of these quantitative methods, those methodologies would not be very would not be very clear to us. So what we need to do is we need to ensure that we are at we are at pace, we are at the same place with respect to this. So this is something that we need to do, right? So ensure that kind of this is done. Okay, so I'll just talk about what exactly Ito's lemma is all about. So I'll just so this is what Ito's lemma is. So Ito's lemma talks about a model or a method to break or to expand a differential equation, a derivative, and from there find out the next idea. So over here, what you see is there is delta f delta t. So it's once differentiating, then twice differentiating, and so on, right? So this is the way Ito's lemma. So as a model, it tries to, or as a method, it tries to find out the path that a variable, a continuous variable would follow by creating the derivatives. So it's a simple expansion rule. So using this Ito's lemma method, or using the Ito's lemma, what we do is we derive the asset equation path, right? So applying Ito's lemma, the the log AT path is obtained. And the log AT path that we get over here is looks something like this. Log A0. So we would not be much concerned about the functional form that has come up, or the mathematical expression, but we would be more focused on its behavior, or on the basic components of this asset path. So we would be more interested to understand how these paths, they or how are these components impacting the behavior of the asset path. So this is how the equation after the asset path has been computed would look like. Okay. So before I proceed, I'll take up a question from Anirudh. So Anirudh asks, do we consider log always of a nonlinear situations only? So most of the cases, when we are developing, say, a time series model, right, or we are developing so a variable which is evolving over time and which is very fluctuating in nature and all. So for those variables, what we do is we do a simple log transformation right at the outset. Now, when we are developing credit risk models, we may not always be doing these log transformations. Log transformations may not always be required. It is not only from the statistical perspective, but also because businesses are more concerned about, or businesses are kind of more concerned about the level values or the original values of the variable. They do not always prefer transformations in their models. So that is one reason as to why this thing is not preferred. So basically, but since over here, we have a differential equation from which we are deriving the asset path. So that is the reason why this log transformation has come up. So if there is something like a rate of change, so over here you are modeling the rate of change of the asset, right? So to get from there to get to the level asset values, that is where we require this particular thing, right? Okay. Okay. So now, from here, the next thing that we start looking into is the following. That so if we look into this asset price path that we have got, so the next question that we try to answer is that why do we need to work on this, right? What is it needed? Why is it needed? So over here, you see that the asset path. So this shows the movement of the asset path, or the equation of the asset path. So corresponding to this, there are the factors which affect the asset path. So let's look into the first component. So it says that log AT is impacted by log A0. So A0 is nothing but the initial value of the asset, or as we call it, the initial assets. Now obviously the asset path that a borrower has, that an obligor will have, will obviously be impacted by the initial value of the asset. Right? So this is where we have the initial value of the asset. Now the next part that we have over here is again the following. That so higher the initial value of the asset is, the higher would be the path of the asset path of the obligor. So basically, this is a kind of an intercept effect. So for example, over here I want to plot the asset paths. Asset path, or so let's put this as time. And over here what I have is assets. So over here, say there is one guy who starts on with A0 star, and over here there is a borrower who starts on with A01. So over here, what we are trying to do is the following. So everything else remaining unchanged, right? The asset path of the borrower who starts off at a higher initial value will always lie above the one who has started off with a lower value. So this is precisely what we call the intercept effect. Known as the intercept effect. So this the very fact that I start on a very initial higher initial capital or a higher initial value implies that I'll start from that. So my asset path will always be higher, right? So for example, if both of them take a same volume of debt, so both of them take a debt which is this straight line. So both of them take this debt. So first of all, what we get to see is that this borrower with this asset path does not qualify for the debt because the debt is beyond his income status. So his income is always lower than the amount of the debt. Therefore, he doesn't qualify. Whereas this borrower, everything else remaining same, has started from a higher intercept point. Therefore, he is a good borrower for this debt and he is like mastering the debt like a boss. So therefore, what we get to see is that this is the intercept. So the intercept impact explains the credibility of the borrowers, right? So in the asset part, the first component which you get to see over here is this A0. Clear? Up to this point, is it clear? The log function, the derivative, yd log at, the result of Ito's lemma, and this explanation. Is it clear up to this point? Let's go through this before we move on with the next one. Clear? So, so talking about this log 80, right? So log 80 is just a transformation of 80, right, of the asset price path. So basically, what you can see over here is that when dy is in the form of dx by x, so dx by x shows the change in x, right? So over here, what will happen is that over here, what I need to do is that over here you have d log 80, right? So let's take it like this. Hold on. So what we have seen is that the first order derivative over here is dy dx, which is equal to 1 by x. Now dy dx equal to 1 by x. So therefore dy is dx by x, right? So what I have done over here is to get this dx by x. What I have done is I have created this. I just have cross multiplied the dx over there. Now what you can see is that dx by x is nothing but d80 by 80, which is nothing but the d log 80. Now if you integrate this, so that depend on the other hand side, so the value that you get for whom you are getting the right hand side will be the log 80. So it's a log transformation of the asset value. So suppose your asset value is 100, log transformation of that asset value will be 2. So it is just the log transformed value of the asset price path. So it's just a ordinal transformation. So that's it. So I mean, there is nothing critical about this. This is just a simple log transformation, right? So is there anything more you want me to explain on this, or I mean, anything more that you are looking out on this part? So this, since there is a fluctuation involved into this value and it's a time series kind of a value, so there will be fluctuations over time. So what we have decided is that we would just do a log transformation so that the fluctuations are kind of smoothened out. So that is all about, right? Okay. So over here, what we can see is that the higher the initial value of the log asset, the better is the, or higher is the value, or better is the credibility of the borrower. Now comes the next part, that is mu a t. So mu a is the average growth rate of the asset prices. So this part talks about the average growth rate of the asset prices. Average growth. So the question that comes out over here is that higher the average growth rate of the asset prices, right? So higher the average growth rate is, the better is the asset price path, or higher will be the asset price path of the borrower, right? So what you need to understand over here is that the average growth, so higher the average growth rate of the firm is, everything else remaining unchanged, the, the credibility of that borrower will be better, right? So in this case, we are saying that higher the average growth rate of the asset price over time, higher is the asset line of the borrower, better is the credibility of the borrower, lower are the chances of default. So let us look into this concept graphically. So what we have over here is this graph. time, and over here what we have is the asset. The asset part. So over here, the next important thing that we need to do is the following. Say both these borrowers start on from the same asset part, right? So let's take this case that so there are two borrowers who apply for the same debt. This is the line of the debt, right? And both borrowers they start from the same asset part over here. So everything else remaining unchanged. What differs is their growth rates, a growth rate of the assets. So the average growth rate is like this. Now for the other one, the average growth rate is negative. So what happens with this borrower is the growth rate of this, the fluctuation is more or less similar. So what you see is that after a point of time, when this guy's asset growth rate grows on, the asset growth rate of the second borrower keeps on going down. That means he is gradually zeroing down on this line. So his chances to zero down on this line is gradually increasing. Right. So his chances of this borrower to default will be increasing, where the chances of this borrower to default is lower. So what we can see is that everything else remaining unchanged. So you can see that the fluctuations around this is around the mean value is more or less similar. The origination point of this, both of them same, they start off with the same asset point. Now what happens over here is that it keeps on changing, right? So what happens over here is that this value it keeps on changing as the average growth rate of the asset price increases. The average growth rate of the asset price for the second borrower keeps on decreasing. So this is how this entire story begins. Clear? So over here, what we get to see is that the second variable, the mu A, is positively impacting the asset price. So higher the mu A, higher the asset price, lower the chances of the borrower to default. Right? Now comes the next part. So this is the impact of the average returns. Impact of the average returns. Impact of the average returns. Now the next thing that we need to talk about over here is that what exactly is this impact. So when I talk about this particular impact, right, so the next thing that we need to understand is how does the volatility or the fluctuations impact the probability of default, impact the asset price path, right, of the borrower. So obviously this will have a negative impact on the asset price path. So that is when the asset price path will certainly increase over time and like sigma square a. So as the volatility increases, the asset price path gets negatively impacted and so on. So this is what we will go to study about, right? So over here, let's draw the next diagram. Sorry. So over here, what we have is the asset price, and over here, what we have is the time period. This is the deadline. Okay. Now, now let's start with the fact that everything else remains unchanged, right? So there is this borrower who starts. So they start on from the same A0. So this is one. So the average fluctuation of this borrower behavior is very less. So the average fluctuation of the sigma A is much lower than the second borrower about whom I am going to draw. If you have a look into this, you will see that. So over here the fluctuation is much more. Therefore, the asset path has greater chances of going down and bumping into the line of default, right? So this curve has a greater chance of going down. Say if I'm to plot this, say for this graph, what I need for this graph to go down, it has to generally come down in this extent, right? Whereas for this particular graph to go down, for this particular line to go down, it will take this much. So this volatile line, it has a greater chance of going down the dead line and getting into a default is much higher than the other guy. So it means that this guy has a very it might have a very it might have the same mean behavior of the asset prices, but the fluctuation is much higher. So the consistency of the behavior of this borrower is much less compared to the first borrower, right? So this is what the overall idea is. Right, so is this part clear, guys? So this is the impact of the standard deviation, the increased volatility or increased variation in the price path. So this is what is right. So if you have a look into this, so if you have a look into this over here, what we are trying to deliver is the impact. Analyze over here is the impact of the volatility. This is the volatility impact of the asset. We have over here is the volatility. Right? So this is the volatility impact. So these are so the initial value of the asset, the mean value, the mean growth rate of the asset, and the sigma square of the asset or the volatility of the asset are the three core factors apart from the Brownian movement which impacts the asset class. Right? And sigma A into WAT, this shows the stochasticity involved within the asset class. Right, so there is a volatility and there is a stochastic volatility involved, so this volatility can vary at any point of time. Right, so these are the core factors which impact the growth of the asset class. Right, so is this part clear? Okay, so the last one says that there is a volatility, right? So you can see that in the blue line, the deep blue line, the movement is very consistent, right? So it's very so the fluctuations about the average value is not very high. But over here, the fluctuation about the value is actually very high. So you see that there are instances when this goes very down and then it goes very high. Then again it goes down, again it goes high, and then again it goes down. So the consistency in the asset path is very less for this light blue line. So now if this line, which is more consistent in behavior, has to go below the debt line, so that the asset path has to fall below the debt line, then what will happen? It must come down to this extent, right? It must come down this much. It's a much larger extent than compared to this line, because this line is always very close, is already close to the debt line, and it needs to go down a slightly lower. So the chances of this light blue line to enter into a default, in the state of default, is much higher compared to this deep blue line or the dark blue line. The reason being that the volatility of the variation in the first line above the mean is much lower than the second line. The second line is much more volatile, right? And hence there is a huge amount of fluctuation. So one time when it is going higher up the average, then it in the second is falling close to the deadline. So what we can see is that the consistency of the asset price path of the light blue line is not very high, right? So this is the reason why this challenge is there. Clear, Anirudh? Great. So over here, the next thing that we need to talk about is that what is the probability of, or when is it that, or on what basis can we say that the probability of, or what would be the conditions there for the borrower to enter into, for the borrower to be, you know, to get a probability of default or to default. What is, how do I estimate that? So now the next thing that we'll talk about over here is we need to estimate our probability of default. So we say that okay, this is the probability of default is when the asset price path AI, or over here the log AT, falls below the asset price, falls below the debt obligation. So when I say this AI, so what I am referring to is the log AT over here, right? So over here what we have is log A0 plus mu A minus half sigma square A plus there is sigma K which is less than Ti. Now over here the next thing that we do is we need to understand that okay, so over here, the question that comes out is one. So Anirudh has a question that if sigma is negatively correlated with asset, then the last part is why is it positive? So Anirudh, that's the Brownian motion, or that's not only sigma, but that's sigma A into WAT. So the value that gets realized, the impact that we would have, would depend on the Brownian motion. That's the stochastic part, right? So that can turn out to be positive or negative. So that's the stochastic part of the asset. So over there I cannot actually determine whether the value is positive or negative or things like that. So over here the only idea is that it's the stochastic portion, right? And that would depend on the, that would explain the behavior of the asset, right? So it's the non, so the sign of this is not deterministic. So depending on the realizations that the Brownian motion would have, right? The Brownian motion would have, it would be positive or negative. So that's the stochastic part. So if WAT is a negative value, that will be a negative value. So this is the sigma A that I'm talking about. The sigma square A over here is the constant, right? And this is the stochasticity about the constant deviation. So this part is the volatility or the fluctuations which happen. Now sigma A is constant, but it says that, so your log 80 is impacted by two parts. One is the initial value, the deterministic component, which is your log a0 and mu a sigma square a. So these are all your factors. But again, there is a Brownian motion, or there is an uncertainty in it which impacts the values. So that third component shows that stochastic value, and that can take any sign depending on what the value of W80 is, right? So that is why we have just generalized it with a positive sign. So when W80 is negative, it is negative. So it's not about only sigma A, it is about sigma A into that Brownian motion value, right? Great. So over here, what we are doing is, so one thing you can see is that all of these are deterministic, right? So it is the value of this, it is this value, the WAT, which plays all the games, which will ultimately determine your probability of default. So it's those factors, those randomness in the behavior, right? The way behavior which varies from borrower to borrower, and you cannot actually so which creates that stochastic, which brings in that Brownian or the uncertainty in the behavior of the asset path is the Brownian motion component. It's the winner component. So that means all we therefore the probability to default will be driven by this particular winner component, right? And this is precisely what we need to identify. So over here we say that the probability to default, this probability to default will be nothing but sigma k WAT less than GI minus. Now, if the asset price path is positively related to this A0, the probability of default will be negatively related, right? Right. So this over here, what we'll do is the next thing is we'll just bring this sigma A with sigma A down. So this whole expression divided by your sigma A. So this is identified as phi of, so where Ci is equal to this entire expression. So this entire expression that we have over here is is Clear on this? So this is said to follow, so Ci follows a normal distribution with mean zero. So this phi Ci, or rather let me put it like this. So the phi over here follows a standard normal distribution with mean zero and radius. Right. So one thing that we can clearly say is that Ci is nothing but the inverse of PD. So therefore, one thing that we can say over here is that this probability of default that we are trying to estimate over here is a function phi of Ci. So Ci is nothing but this particular expression. So there is no such name as Ci. So you can think about it as Ci being a value that, or a realization that this minor variable takes. So it says that, say, probability to default is, so probability that the minor process takes a value which is less than this. So if the minor process takes a value greater than that, then there would be no default because the asset value would be above the default value. So this, what we are trying to do over here is we are trying to understand that what exactly is the probability of the account to default, right? So that we saw that it is the minor value, minor process value, which is making this, which is creating this difference, right? So over there, what we need to assure, what we need to understand over here is that for what values of W will the probability of default be higher. So this is precisely what we are trying to understand over here. That for what, for there, so there's a certain range of values for the wind up process. So for values below that, right, there will be a default. Values above that, there will not be a default, because for a certain, after a certain value, for a some sigma over some value over this part, right, the log 80 will be higher such that it is above the default line, right? So that is where this W80 will not be impacting the borrower to default. But if W80 is below a certain value, then the asset log asset or the log 80 will be below a certain value, and there the default may occur. So this is precisely what the idea is. Clear? Okay, so Vishal has a question over here that why is half using the equation? So this comes as a result of the Ito's lemma derivation, Vishal. So we'll take this expression as given, right? So sigma square by 2. So it generally comes as a part of the Ito's lemma derivation. So if you want to go through this derivation, you can go through it. You'll get the idea clearer, right? So this is how. So this is what the PD is all about, right? So I will not proceed further with this today. So we'll take a pause over here. I'll send over this document to you right now, right? I'll record the sessions today. The session will be recorded today, end of day. I have to convert these recordings. I'll share over the recordings, go through the recordings of these 2 days over the week, right? Get your doubts in place and get back to me over the week. Then we'll continue it on Saturday because this is a very critical concept, right? We need to understand this concept, and barging too much together in your mind would be difficult because the calculus concept needs to come in, the calculus part that needs to come in, and so on. So this is something that we need to work around. So work on this part very carefully because this is understanding the ASRF model is very important from the interview perspectives because say suppose someone now the generic interview question is what are the steps of a PD model development. Now what if someone comes and asks that what exactly is the difference between the Basel PD and the behavior scorecard PD that you develop? What is the difference between a PD model and a you know through the cycle and a point in time PD. What are the basic assumptions on which the Basel model stands? So this part will be answering these questions. And if you are trying for captives, they are bound to ask you these questions, right? So therefore, this part that we are discussing over here, and this part we'll be discussing over the next 2 classes next week. These are the core, the heart of the Basel model. So we'll go slow but steady in this part. But I need everyone to be very, very, very clear on what is there in the part, right? So I'll record this. I'll send over the recordings today, right, for the last 2 classes, and but go through this part very nicely. I'll just I'll just do this part. Thank you. We'll meet next week, and in between, if you find any problems, please reach out to me. We'll get that immediately clarified. Thank you.